Welcome back, everyone. In the last lesson, we learned about the electrophilic aromatic substitution reaction and mechanism, and we also learned about one type of EAS reaction, that is, the halogenation of benzene rings. In this lesson, we're going to learn several other types of electrophilic aromatic substitution reactions, and we're going to start here with nitration. The nitration of benzene derivatives allows attachment of the heteroatom nitrogen to an aromatic ring. This can be accomplished by treatment of the aromatic system with a mixture of sulfuric acid and nitric acid. In this way, the oxidized form of nitrogen, called a nitro group, is attached to the aromatic ring. While the nitro group itself is not very biologically interesting, in fact, we don't see nitrated aromatic rings occurring in nature, the nitro group itself can be reduced to an amino group. And it turns out that aromatic amines are very biologically important. And this is why the nitration of aromatic rings is an important reaction. It gives us a starting point to generate aromatic amines. Let's take a look at the mechanism for how nitration actually occurs, and then I'll show you some of the reduction conditions that would enable us to transform the nitro group into an amino group. As with other EAS reactions, the first step in the mechanism is generation of the strong electrophile that will go on to react with the benzene ring. In the case of nitration, the electrophile is called a nitronium ion, and a nitronium ion is an NO2 with a positive charge. This nitronium ion is a very strong electrophile, and it's formed by the reaction between nitric acid and sulfuric acid. Here's what it looks like. While nitric and sulfuric acids are both strong acids, sulfuric acid is slightly more acidic with a pKa of -3. Compare this with nitric acid's pKa of -1.5, and we can see why a proton transfer is possible between sulfuric acid and nitric acid. If we look closely, we can see that this protonated form of nitric acid now has a good leaving group on it. We've converted the hydroxyl group into potentially a water molecule if we can undergo loss of leaving group, which is exactly what happens next. We can push the electrons from this negatively charged oxygen to the nitrogen atom that's positively charged, and then kick off a water molecule. So this is how we can generate the nitronium ion with sulfuric acid and nitric acid. Now let's take a look at how the nitronium ion reacts with benzene to see how the EAS part of this reaction works. Because nitronium ion is such a strong electrophile, the aromaticity in benzene can break temporarily to form the sigma bond from one of the pi bonds. The intermediate which forms from this step is a resonance-stabilized carbocation, and by loss of a proton, we can reform the aromatic ring. Mechanistically, we can show hydrogen sulfate acting as the base in this step to remove the ipso proton. When the ipso proton is removed, the electrons in the sigma bond go in to form a pi bond, therefore reestablishing the aromatic ring. We now have a nitrated benzene. On a practical level, the nitration of benzene and other aromatic rings is a fairly straightforward procedure. Typically, we just combine the aromatic ring with the nitric acid and sulfuric acid solution. As the reaction is typically exothermic, there's not usually a need for any excess heat, but we do use a reflux condenser so that the reagents, as they evaporate, are condensed back down into the flask. It is important, however, to exclude as much water as possible from the reaction environment. Water will react with the nitronium ion, pushing the equilibrium back a little bit, and if we want the reaction to produce as much nitronium as possible, that's undesirable. Optimal yields for this reaction, therefore, can be achieved by things like flame drying the reaction environment, using drying tubes, and distilling reagents before using them. The nitration of benzene is done on a large scale industrially. And of course, these industrial reactors are much more massive in scale. After the reaction is complete, it's necessary to quench any excess nitronium as well as extract the organic material from the acidic environment. This is usually done with an organic solvent, as the nitrobenzene or other nitrated aromatic compound is usually soluble in organic solvents. As I mentioned earlier, it's possible to reduce the nitro group on an aromatic ring to an amino group, and several conditions for that are available. While we're not going to go through the mechanisms for these transformations at the moment, I want you to be aware of them so that you can use them as tools in the event that you need to convert a nitrobenzene or some other nitrated aromatic ring into an aromatic amine. Some of the most common methods for reducing nitro groups to aromatic amines include the use of various transition metals. For example, we can use iron as it's easily oxidized by the nitro group in the presence of acidic water to convert nitrobenzene into aniline. Another really common set of methods involves the use of various reducing agents. For example, we can hydrogenate a nitro group using hydrogen and palladium catalyst. We can also use sodium borohydride or the stronger lithium aluminum hydride if the other methods resist reduction. We'll be looking at the way these reactions work later on in the course, but for now, just be aware of the conditions and what they allow you to do so that you can recognize them and use them as tools in your toolbox. Let's go on to the next page and learn another of the EAS reactions, that is sulfonation. Similar to how nitration of benzene rings and other aromatic rings doesn't occur in nature, neither does the sulfonation. That doesn't mean, however, that sulfonation of aromatic compounds is not incredibly important. Various practical applications of aromatic sulfonation include the production of sulfonated pharmaceutical products, strategic tools in organic synthesis, and to make different types of polymers and other materials. Let's take a look at the conditions and mechanism for aromatic sulfonation. Aromatic sulfonation can be accomplished by treating the aromatic system, such as benzene, with a mixture called fuming sulfuric acid. This fuming sulfuric acid is prepared by saturating sulfuric acid in its concentrated form with sulfur trioxide gas. In addition to its use in the sulfonation of aromatic rings, fuming sulfuric acid, also known as oleum, is used in the manufacture of explosives and in certain applications where very strong oxidizing reagents are necessary. In the presence of sulfuric acid, sulfur trioxide is protonated to form the electrophile that our aromatic ring will react with. Specifically, aromaticity is broken when a pi bond from the aromatic ring forms a sigma bond with the sulfur atom of the protonated sulfur trioxide. It's this resonance-stabilized carbocation intermediate that is deprotonated by a hydrogen sulfate anion to reform the pi bond and the aromatic system. After quenching the reaction, the sulfonated aromatic product can be cleanly isolated by extraction into an organic solvent such as dichloromethane. As is mentioned in the textbook, the formation of a phenol involves the direct hydroxylation of an aromatic ring. Unfortunately, this type of reaction is fairly difficult to perform under normal organic reaction conditions. However, direct hydroxylation of aromatic rings does take place in biological systems with the aid of enzymatic reactions. The textbook shows an excellent example of this, that is the direct hydroxylation of para-hydroxyphenyl acetate into 3,4-dihydroxyphenyl acetate. The key steps in this reaction are shown here. The reduced form of flavin adenine dinucleotide, that is FADH2, reacts with molecular oxygen. This gives a hydroperoxide intermediate shown here. This is where our electrophilic aromatic substitution mechanism starts to work. The protonation of this peroxide results in the formation of a strong electrophile, and this is where the aromatic ring will react, breaking its aromaticity. We then see the familiar reestablishment of the aromatic ring using a base to deprotonate that ipso proton to form the pi bond from the sigma. This all happens so fast it's easy to lose track of where that hydroxyl group actually came from. Notice it came from the fact that molecular oxygen reacted with our FADH2 at this bond to form our hydroperoxide intermediate. That's actually where that oxygen comes from. It's molecular oxygen. And in general, this is a very common way that biological systems use to make molecules more polar. So you start with something that doesn't have a hydroxyl group, and you want to metabolize it or eliminate it from the system to make it more water soluble. You hydroxylate it. making it more polar. So that's an example of one of the many tricks that enzymes have up their sleeves. They can do things in biological systems, in cells, that we can only dream of doing in much shorter steps and much more elegantly. We will see an example of how we can hydroxylate an aromatic ring a little bit later in this chapter, but for now, just note that it's not easy to do in the lab. One of the most important electrophilic aromatic substitution reactions is called the Friedel-Crafts alkylation. We're actually going to be learning two different Friedel-Crafts reactions, the alkylation and the acylation. Let's take a look first at the alkylation reaction. In an alkylation reaction, we're making a carbon-carbon bond between an alkyl group and some other type of carbon. In the case of the Friedel-Crafts reaction, we're forming a carbon-carbon bond between an alkyl group, which I've called R, and a carbon atom on an aromatic ring, such as benzene. That's what we would call an aryl carbon. So we're forming an alkyl-aryl bond in the Friedel-Crafts alkylation. This can be accomplished by using a Lewis acid, such as aluminum trichloride, in the presence of an alkyl chloride. So, for example, suppose we wanted to convert benzene into tert-butylbenzene. We would need to alkylate the benzene ring with a tert-butyl group. To accomplish this reaction, we would need to use an alkyl chloride, specifically tert-butyl chloride, in the presence of aluminum trichloride. Let's take a look at the mechanism for how this specific example actually works. First, I've drawn out tert-butyl chloride and the Lewis acid aluminum trichloride. Aluminum trichloride is, of course, electron deficient because it only has 6 electrons rather than the 8 that would be necessary to fulfill the octet rule. Therefore, it has an empty p orbital, which is excellent for accepting an electron pair. So, for example, the electron pair that comprises the covalent bond between chlorine and the tertiary carbon atom of tert-butyl chloride breaks to form a new bond between aluminum and that chlorine atom. This, of course, leads to the formation of a carbocation intermediate, which in this case is a relatively stable one as it is a tertiary carbocation. It's this carbocation intermediate, however, that acts as the electrophile in an electrophilic aromatic substitution reaction with benzene. So as we've seen before, the aromaticity in our benzene ring can break when one of the pi bonds reacts with the electrophile to form a new sigma bond from a pi bond. Aromaticity can be reestablished when aluminum tetrachloride depregnates that ipso proton. Therefore, we see the formation of our tert-butylbenzene and hydrochloric acid as a byproduct in this reaction. So at first glance, this looks like a very powerful method for making carbon-carbon bonds at aromatic rings. However, there are some important limitations of the Friedel-Crafts alkylation that you should be aware of. Let's take a look at a few of those limitations below. One of the first limitations is in terms of scope. It turns out that only alkyl halides can be used successfully in Friedel-Crafts alkylations. What that means is we need to have an sp3 hybridized carbon atom attached to the halide. So unfortunately, in Friedel-Crafts alkylations, we can't use substrates like a vinyl chloride or other aromatic chlorides because they don't form stable carbocation intermediates if a chloride atom were to leave that sp2 position. So that's one limitation. Another one is that we cannot perform Friedel-Crafts alkylations if there's an electron withdrawing group attached to the aromatic ring that we're trying to alkylate. So for example, if we had nitrobenzene and we applied the same alkylation conditions that we saw for benzene, we don't see attachment of the tert-butyl group to the aromatic ring. In fact, no reaction takes place. You're going to see the specifics of why this happens a little bit later in this chapter, but for now, it might be helpful to remember that there's no FC with EWG, and EWG is called an electron withdrawing group. Now, we did previously discuss the differences in structure between electron withdrawing and electron donating groups, but here are a few other examples of groups other than nitro that prevent Friedel-Crafts alkylations from occurring if these are already attached to the aromatic ring. Now, another interesting limitation of Friedel-Crafts alkylations is that it's very hard sometimes to stop the reaction from going overboard. By that I mean we often see multiple alkylations on a single substrate as the major product. So, for example, I just showed you above the reaction between benzene and tert-butyl chloride, and we went through the mechanism to show the formation of tert-butyl-benzene. The only issue with that is that tert-butyl-benzene is actually the minor product in that reaction. The major product is the dialkylated product, that is a tert-butyl group on two positions in the benzene ring. Now, you're going to soon learn why this actually happens, but for now note that these alkyl groups actually activate the benzene ring to accelerate further reactions of it. So the monoalkylated benzene ring reacts faster than benzene alone, which is why we see the dialkylated product as the major product. And this is very common with Friedel-Crafts alkylations. Now, a final limitation of the Friedel-Crafts alkylation has to do with the fact that the reaction involves the formation of a carbocation intermediate. Because we're forming a carbocation intermediate during the course of the reaction mechanism, that means this reaction is susceptible to carbocation rearrangements. As a consequence of this, it can be impossible to make certain types of aromatic derivatives using the Friedel-Crafts alkylation. So, for example, in this molecule, where we have a linear alkyl group attached between the aromatic ring and a primary carbocation, is impossible with Friedel-Crafts alkylation. The reason why it is impossible is because carbocations that are primary tend to rearrange to more stable secondary and tertiary carbocations. So, for example, suppose you set out to synthesize this N-butyl substituted benzene derivative. What you need to do as far as Friedel-Crafts alkylations go is take a benzene ring and treat it with aluminum trichloride and N-butyl chloride. These would be your typical Friedel-Crafts alkylation conditions. Unfortunately, however, when you isolate the organic products, you find that the major product is not the one that you were trying to make. In fact, the major product is actually a sec-butyl benzene rather than N-butyl benzene. We've attached the butyl group at the secondary carbon rather than the primary carbon. Pause the video for a moment and see if you can put together a mechanism which explains this result. First, our N-butyl chloride reacts with the Lewis acid aluminum trichloride to form the primary carbocation and aluminum tetrachloride. It's this primary carbocation that's the problem. We have a primary carbocation here right next to a secondary carbon atom. The molecule can rearrange to a more secondary carbocation by a simple 1,2 hydride shift. The secondary carbocation is more stable than the primary carbocation because that carbon, which is positively charged, is surrounded or attached to more alkyl groups. And remember, the more alkyl groups are attached to a carbocation, the more stable it is. That happens because of something called hyperconjugation. In hyperconjugation, the alkyl groups donate some electron density to that empty p orbital on the carbocation, therefore stabilizing it. So when all is said and done, our primary carbocation has rearranged to a more stable secondary carbocation, which is what reacts with the benzene ring in the electrophilic aromatic substitution reaction that we've already seen. This is why it's impossible to form as the major product primary alkylated benzene rings using Friedel-Crafts alkylation. I'll show you a workaround for this a little bit later in this chapter, where we can perform the Friedel-Crafts acylation followed by a reduction in order to obtain these primary alkylated products. Let's go to the next page though, and first learn what a Friedel-Crafts acylation actually is. In a Friedel-Crafts acylation, we are attaching, instead of an alkyl group, something called an acyl group. And I've drawn an acyl group here for you. An acyl group is a functional group that's composed of something slightly more fundamental called a carbonyl group. A carbonyl group is a functional group fragment that consists of a carbon doubly bonded to an oxygen. We call this part a carbonyl group. When a carbonyl group is attached to an alkyl group or an aryl group, one on each side, we call it an acyl group. So it looks kind of like a ketone because we have two R groups on either side. So a Friedel-Crafts acylation looks something like this. We're taking an aromatic ring, like benzene, and we're attaching one of these acyl groups at one of the carbon atoms of the benzene ring. The chemistry for Friedel-Crafts acylations is very similar to the chemistry of Friedel-Crafts alkylations. However, instead of using an alkyl chloride, as we did in Friedel-Crafts alkylation, here we're using an acyl chloride. An acyl chloride is, of course, very similar to an alkyl chloride, except instead of having an alkyl group attached to the chlorine atom, we have an acyl group, meaning we have a carbonyl with an R group on one side. The Friedel-Crafts acylation also requires that we use a Lewis acid like aluminum trichloride. So for example, suppose we wanted to acylate a benzene ring to form acetophenone. We've got this acyl group attached to benzene, so in order for us to perform the Friedel-Crafts acylation, we of course need aluminum trichloride and another reagent. See if we can draw the acyl chloride that we would need to use in this reaction. If you need a hint, I've highlighted the fragment we're attaching here in purple. That's the part that we need to attach to the chlorine atom in order to have the right acyl chloride for this reaction. And there we go. We would need to use this molecule, which is called acetyl chloride, in order to attach this particular acyl group to benzene. Let's take a look at the mechanism for how this reaction takes place. In the first step of the reaction mechanism, we have our Lewis acid, aluminum trichloride, and our Lewis base, which is the acetyl chloride. We can show the bond breaking between our carbon atom and the chlorine atom, and a new bond forming instead between aluminum and chloride. This first step results in the formation of our strong electrophile, which is called an acylium ion. And because this acylium ion is such a good electrophile, we can show the aromaticity inside of benzene breaking in order to convert one of the pi bonds into a sigma bond at the acylium carbon atom. This results in the formation of a resonance-stabilized carbocation intermediate that can be deprotonated at that ipso position in order to reestablish aromaticity. In the end, we form our acylated benzene, which can be easily extracted using organic solvents following an aqueous workup. Now, one thing that I want you to notice here is that this acylium ion is not subject to the same types of rearrangements that an alkyl carbocation would be. What that means is that acylium ions aren't going to rearrange through things like hydride shifts or alkyl shifts. And that means, as you will see soon enough, that we can do certain things with Friedel-Crafts acylations that we simply can't do with Friedel-Crafts alkylations, making this version of the reaction significantly more versatile than the other. With that, I'm going to end this lesson. In the next lesson, we'll learn a little bit more about aromatic reactions and what happens if we already have substituents on an aromatic ring and we want to perform some of these EAS reactions. I hope you're doing well. Please let me know if you have any questions, and I will see you soon.